Good afternoon, everyone. Welcome to the HPL seminar this week. Today is my great pleasure to introduce our speaker, Dr. Koen Lemaire. Koen received a Bachelor of Science degree in 2011 at the Vrije University Amsterdam in Netherlands. Then he started master's course at the same university in the program of Human Movement Science under the supervision of Dr. Knuk van Zwist. During his master's, Koen primarily worked on the applicability of the Huxley muscle model to musculoskeletal modeling. After he received Master's of Science degree in 2014, Koen decided to keep building his academic career by continuing his work as a PhD student under the same supervisor. His research topic was about modeling and measuring muscle mechanics and energetics, which I think if I'm not wrong, he gave a presentation in the HPL seminar a couple years ago when he was a visiting student here at the University of Calgary. After he received the PhD degree last year in Netherlands, and he came back to Calgary to do a postdoc working with Dr. Art Kuo. Currently, Koen has been interested in muscle modeling, comparative biomechanics, and motor control, which is somewhat related to the presentation that he'll be giving today. When I asked him about non-scientific and interesting facts about himself, he gave me 5 different fun facts, and I found one of them seems to be very interesting. He said he received a free drink at a bar in Calgary for dancing on a stage to ABBA's Dancing Queen. Now, so many questions came to my mind, but I'll ask him later on. Today, Koen will be giving a talk, which is about soft tissue work in human locomotion, quantitative tests, and theoretical underpinnings. All yours.
Thanks, Seungwon. Let's see. Great. Yes, so I'll be talking about soft tissue work in human locomotion today. And so in biomechanics, most of us, I guess, are in the business of doing biomechanics, and biomechanics usually involves some mechanical analysis of human movement with the aim to establish the relationship between form and function, to answer questions about motor control and what have you more. And a key assumption in this biomechanics modeling is that the human is considered to be a collection of rigid bodies, so undeformable bodies. And I wondered what happened when that assumption breaks down. And I have a little bit of experience with that myself. So this was, I'm the person on the right here, who is, I think, about to receive a fair amount of kinetic energy, which I need to absorb with my soft tissues. And at that point, I realized that my body is not as rigid as I might have hoped. And perhaps that's a good thing, because that allowed me to dissipate that energy. And a more mundane example that maybe strikes closer to home for you guys is, of course, running or walking. So this is a slow motion video of a person running on a treadmill barefoot. And as you can see, there's a fair amount of deformation happening in this foot. And the question now is, well, obviously this matters. And the question is, what should be the consequences for this deformation for our biomechanical analysis? Now, of course, I'm not the first person to ask this question. So Carl Zellick and Art Kuo established a method to estimate this energy dissipation as the difference between total mechanical energy and joint work. And this was later expanded upon by Xiao Yu, who's undoubtedly in the audience, who showed that soft tissue work is increased in obese people, which suggests that this has something to do with a wobbling mass, let's say, which is dissipating energy. And later, Eric Honnert and Carl Zellick further developed this and found that perhaps most of this soft tissue work is actually due to tissue deformation in the foot, as we saw in this video also. And so you can imagine that there's all kinds of dissipation happening in your viscera, in your muscles, and in joints, which are maybe not captured by a rigid body model. And another part of at least inverse dynamics literature, which has been talked about a lot, are what's called dynamic inconsistencies or residual forces. And I'll later explain in detail what this means, but I'll just briefly illustrate it now. So if you are doing inverse dynamics analysis on a human, you're measuring ground reaction force and motion capture, but it is not guaranteed that these things actually agree with each other, because both describe the motion of the center of mass, and that motion might not be the same based on your kinematics and your ground reaction force. Now, one way to solve this was actually also conceived by Art, which is some sort of optimization where you tweak the system a little bit such that it becomes consistent again. And I was wondering, is there a relationship between this well-known residual forces and the soft tissue work? And it turns out that there is, and we're going to explore that today. So the aims for today's talk, I will try to do a quantitative test of soft tissue work calculation, because previously, previous work was done on, for instance, obese people, comparing obese people to non-obese people, or walking at different speeds, but there has never been a sort of independent quantitative test of such a calculation. Then the second aim for today is, can we establish this relationship with residual force or moment, and what does this all mean? And then, of course, we are interested in which anatomical structures are responsible for dissipating this energy. Okay, so question one, quantitative test of soft tissue work. So the basic question is, can we back calculate a known amount of dissipation when we introduce that to the system? Now, as promised, I first am going to go into a little bit of theory, just so that everybody is on the same page. And this is, of course, fun. So inverse dynamics analysis one-on-one. So you measure motion capture and ground reaction force, and then you make some model of the human, usually a rigid body stick figure. And then you apply the laws of mechanics to get stuff like joint moments, joint reaction forces, joint powers, etc. So let's focus on these mechanics. So the mechanics for a non-rigid body, as we all know, are governed by linear and angular momentum balance. So linear momentum balance says F equals ma, or the sum of the forces equals the mass of the center of mass times its acceleration. And angular momentum balance is something similar, that the sum of all moments acting about a point equals the rate of change of angular momentum about that point. Okay, and when you think of momentum, you should think of mass movement, like a train, like a large freight train driving at a high speed has a lot of momentum. Okay. And in our analysis, when we do inverse dynamics analysis, the sum of forces we measure is ground reaction force and gravity. So we measure this, right? And then the mass times acceleration of the center of mass, you could argue we also measure, right? Because we have a model and we do motion capture. And so in some sense, we have two independent measures of the same thing. And the difference between those two, I mean, in theory, they agree, but in practice, they will not, because they're both measurements. And the difference, this is what people call dynamic inconsistency or residual forces, or some people frame it as an overdetermined system. You have basically more knowns than unknowns. You have too many knowns, etc. Okay, now what are the consequences for this in terms of energetics? Now it gets a little bit complicated, but bear with me. So let's start with a single rigid body. Now, the mechanical energy balance for a single rigid body says that the work done by all forces that act on that body equals the change in kinetic and potential energy. Now, this is no rocket science. And then for a multi-segment body, things get a little bit more complicated because there you have external forces, but you have also internal forces, so forces acting between segments that can do work. And both of these work terms again equal the change in total mechanical energy. So the essential difference is that in a multi-segment body, internal forces can do work, joint work, because these segments can move with respect to each other. You have joints, right? Okay. So this is the mechanical energy balance for our whole human. And what does this mean in terms of walking? Well, this external work is basically the work done by the ground reaction force, which is approximately 0 during level walking. This internal work is joint work, right? So that's the work done by your muscles, basically. And that's calculated assuming rigid segments. And then the right-hand side, so the change in mechanical energy, you can formulate as the change in energy of the center of mass, plus the kinetic energy relative to the center of mass, where this center of mass energy is based on the ground reaction force. And so this does not have a rigidity assumption. Now, in the ideal world, these two would equal each other. But just as we have dynamic inconsistencies in our mechanics, these inconsistencies also lead to these two terms not equaling each other. And the difference is defined as soft tissue work, right? So soft tissue work is the total mechanical energy estimated by center of mass work plus kinetic energy relative to the center of mass minus the sum of all our joint work. Okay, now we can get back to the question. 3 deep breaths. This was difficult, but I hope you guys followed that. So to answer the question, to do a quantitative test of this soft tissue work, I did an experiment where I deliberately added soft tissue work by means of a camping grade air pump, which was tied under the feet. And we, with this air pump, we walked at different speeds on a treadmill, and we measured ground reaction force and kinematics as per standard, you could say. And apart from this, we did an independent experiment of the air pump to quantify the work associated with one compression of the air pump. Okay, so I just want to show you guys this movie, and I hope you also can hear this. So as you can see and hear, there is massive dissipation going on. There's sound, noise, airflow, compression, contraction, what have you more. And so I would say that this is a good intervention to introduce dissipative soft tissue work experimentally. So let's look at the results of these experiments. What you see here is each line here represents the average of about 40 strides aligned with left heel strike. And this is on the x-axis here, you're looking at percentage of gait cycle. So 0 is left heel strike and 100 is again left heel strike. And then different lines represent the different speeds. And the left leg is represented by the red lines or the first hump, and the right leg is represented by the green lines. And what we're looking at here is ground reaction force in the vertical and fore-aft direction. So vertical are the higher amplitude signals for a normal walking and air pump walking. And this is ground reaction force in body weights. And this looks, I would say, pretty normal. At least for the normal walking, this certainly looks normal. So we have a nice double humped ground reaction force profile as we expect. And then we can also look at the, from this ground reaction force, we can calculate center of mass power. And that's what we are looking at here. And this also looks pretty normal with a push-off, with a nice collision and push-off around double support. And then for the, we can combine this center of mass power with this peripheral energy, and then we get our estimate of total mechanical power, or total rate of change of total mechanical energy of our body. And that's what we see underneath here. And then we see that there's somewhat larger energy fluctuations in the air pump. Okay, and what does this mean for our soft tissue power? Well, we define soft tissue power as the difference between this total mechanical power and the sum of joint powers. And if we look at this difference for both conditions, then we see that in the air pump around early stance, there's actually a pretty large difference. And that also leads to large soft tissue power in the early stance phase for the air pump. Now we can integrate this power over time and then we get work. And that's what you are seeing here. So here, again, left is normal walking, right is air pump walking. And now we are looking at net work per stride on the vertical axis and treadmill speed on the horizontal axis. So for each condition, we have a number here. And then we see that net mechanical energy hardly changes over strides, which is what we expect. But our sum of joint work is positive, and consequently, our soft tissue work is negative, just as we expect, because this air pump is dissipating energy. Now, we want to test this against an independent measure of the air pump dissipation. And for that, I did a very simple experiment where I just pressed on the air pump. And then I estimate the position of the point of application of this force as the mean between these two markers. And then assuming a massless pump, we can calculate the amount of positive and negative work done during such a compression. And if we plug that into this figure, we see that it fairly well agrees with our soft tissue work estimation. So it's a slight underestimate, but that's not a total surprise because we have also some soft tissue in other structures, perhaps, during this experiment. Okay. So that was the end of part one, our quantitative test of soft tissue work. And I would say that our calculation agrees fairly well with an independent quantitative measure. So how about question two? Well, our expectation, first of all, is that if we have increased residual force, we have increased soft tissue work because of these increased inconsistencies. And the question, yeah, okay. So to address this question, I look at a similar experiment where I do, but now just normal walking, so no air pump, but over a larger range of speeds. And we expect that these higher speeds result in larger ground reaction forces. That's now rocket science. Larger energy fluctuations. That's also probably going to come true. More soft tissue work and larger residual forces. So let's see, let's look at the data for this. So this figure you are by now familiar with. So in the top panel, we have ground reaction force. In the middle panel, we have our center of mass work, or power, sorry. And in the lower panel, we have center of mass plus peripheral power, which is the rate of change of total mechanical energy. And now lighter shading indicates faster speed. So the higher peaks here are associated with faster speeds. And so we indeed see larger ground reaction forces. We see larger energy fluctuations clearly with speed. And do we also see more soft tissue work? Well, let's look at our soft tissue work figure, or soft tissue power. And indeed, we see that for the normal walking case, we have higher soft tissue powers for faster speeds. And this also translates into higher net soft tissue work when we integrate that power over time, which you can see in the left panel here, which is now expanded with more speeds. So we have more soft tissue work. Now, how about these larger residual forces? That's shown here. So in the top panel, we have our ground reaction forces again. And now in the middle and lower panel, we have the magnitude of the residual force and the residual moment. So again, this residual force is the difference between basically MA estimated, so mass times acceleration estimated from the motion capture and the force plate. And we see that indeed this difference gets much larger with higher speeds. And also the discrepancy in the angular momentum balance equation, which is the lower panel, also gets larger with higher speeds. So we do have larger residual forces. And are these residual forces then also related to this soft tissue work? Well, if you look at the left panel here, you do get that impression. So we have these peaks in soft tissue power, which more or less coincide with peaks in the residual force and residual moment. However, for the air pump condition, that does not appear to be the case, right? So we have a lot of soft tissue power in the air pump case, but not a lot of residual force. And we can actually explain that. So imagine that the air pump is a massless damper. So the air pump has no mass, but it can dissipate energy. Well, if it has no mass, it will not show up in our force equation, right? So it will not contribute to a discrepancy in the force equation, but it will contribute to energy dissipation. And so the conclusion of that is that residual force is actually only affected by wobbling mass and not by a massless damper. Okay, so to wrap up part 2, is there a relationship with residual force? I would say yes, for the wobbling mass, but not for a massless damper. Now to the last part, which anatomical structure is responsible for dissipating all this energy? Actually, there has been evidence, as I indicated previously, that this might happen in wobbly mass, and this evidence mainly comes from Xiaoyu's 2015 paper, where he showed that soft tissue work is increased in obese people. Furthermore, we see it has been shown before, and also in this work, we show that soft tissue work is increased with speed. And we show in this study that speed is related to larger residual force, and large residual force is indirect evidence for wobbling mass, right? Because that's basically a mass times acceleration term that is not captured in our rigid body model. And so altogether, I would say there is evidence for wobbling mass as a source of energy dissipation. However, as we saw in the video before, and I hope it renders well on your screen, if you look carefully, you actually also see pretty substantial deformation of the heel pad and the foot. And the question is there not also a lot of energy dissipated there? Well, this has actually already been figured out more or less. So Eric Honnert and Carl Zelig quite recently published a paper where they show that the foot and shoe is responsible for the majority of soft tissue work in early stance. And if we look at, so they figured that out by computing a term that's called distal foot power. And I did the same. And if you look at the distal foot work, so we're looking at the left panel, normal walking, and now there's an added term here, distal foot work. You actually see that this distal foot work changes in the same direction as soft tissue work. And for the air pump case, actually the squares here are on top of the circles. So for the air pump case, distal foot work is a very good estimate of soft tissue work. And so that suggests that also deformation of the heel pad contributes to soft tissue work. Yes, so for air pump perfect match and for normal walking, certainly in line with HONOR 2019. Okay, so I just want to briefly highlight some more points and then wrap up because it's super nice weather, of course. There's one thing that is a bit tricky in all of this, and that's the definition of soft tissue work. And I will talk about that next. And another thing I want to talk about is other sources of modeling error and perhaps the relation to this optimization approach that I talked about previously. So people wanted to solve these dynamic inconsistencies by doing some optimization, and perhaps we can still say something about it. Okay, so the first thing that is a bit problematic is that joint torque or power or work or what have you is not uniquely defined when you do inverse dynamics in an inconsistent system. And the reason is that the joint torques that you calculate depend on which segment this residual force or moment is assigned to. So as an example, in standard inverse dynamics, you will start at the foot and compute force and moments balance for the foot, and then move to the shank, and then move to the thigh, etc. And then when you arrive at the head, you have something what's called a residual force that's appearing at the head, right? This is the standard way of doing it. But you can conceive, I mean, you could say, well, I can also start at the head, and then this residual is appearing at the feet. And then you obtain actually a different result. So your ankle torque will be different in both of these conditions. And of course, in the second condition, you're not using the ground reaction force, so you could argue that that's a bad idea. But there's also nothing, I mean, there's no principled reason why this residual force needs to apply to the head. And what is best will probably depend on details of the system, but we do not know these details. And so this is a bit of a theoretical issue with this soft tissue work, although I think it is not an issue in terms of the practical application as we've shown in this talk. I mean, we can estimate the dissipation, for instance, by this air pump. Okay. So are there other sources of error that might contribute to this? So this discrepancy between, on the one hand, ground reaction force, and on the other hand, kinematics and our model might just be due to misestimating inertial parameters. So let's say that you believe that your shank is 3 kilogram and your thigh is 5 kilogram, but in reality, your thigh is 6 kilogram and your shank is 2 kilogram, then you of course make mistakes in your inverse dynamics calculation. But I believe that that will only introduce transient effects because if it's periodic motion, your net kinetic energy change is zero, and thus it will not affect the net joint works. Okay. How about noise? Well, of course, noise can affect results, but this is unlikely to be systematic when it's noise. And how about skin artifact? Well, marker motion relative to bones might explain soft tissue work. But if that explains it, then that's actually what we are interested in, right? Because this marker motion relative to bone is exactly the type of mass motion that is dissipating energy. Okay, so to wrap up, I talked about soft tissue work today and shown that it represents foot deformation and wobbling mass. We did a quantitative test of this soft tissue work calculation where we showed that it more or less agrees with that quantitative test. We talked about relationship with residual force and moment, and there seems to be a clear relationship with residual force, but only in the case that you have wobbling masses. So for a massless damper, this relationship obviously is not there. And where is the energy dissipated? Well, this is frankly still a bit of an open question, but based on the literature and on this study, I would say it's most likely in the foot and in wobbly masses elsewhere, depending on maybe the anatomy of the subject. Okay, I want to close with acknowledging discussions with Eric, which has been a great help in figuring all of this out, and of course discussions with my many QuoLab colleagues who have also contributed to my understanding. And with that, and I would of course like to thank you for showing up in this weather, and I'm happy to take any questions.
Thank you very much, Koen, for giving an interesting talk. So if you could now unshare your screen so we could see each other. Yeah, thank you very much. So I also would like to kindly suggest everyone to turn on the camera during the discussion period if you feel comfortable with it. Yeah, I think it'll give us a bit more active discussion period. Thank you for doing that. So if you have any questions for Koen, please use the icon raise hand button. So you can find this when you go click reaction icon at the bottom of your Zoom screen. If your Zoom version does not have that icon over there, then please also feel free to send me a Zoom message via Zoom chat. Then I'll call on you when it is your turn. Now the floor is open for the questions. Yes, Brent, please go ahead.
Thanks, Seungwon. Thanks, Koen. That was a great talk, thought-provoking talk. I want to talk a little bit more about the noise effect, and I have some questions about how you processed some of your data, specifically like the motion analysis data and the ground reaction force data. How are they filtered? What were the cutoff frequencies?
Good question. Motion capture 20 hertz and ground reaction force also 20 hertz.
So identical cutoff frequencies.
Yes.
Okay. Well, then my second question, I don't have my follow-up question because obviously filtering those signals at different frequencies could also introduce a systemic effect in the residual forces as a function of speed.
Yes, of course. Yeah.
Okay. All right. So that was.
Yeah. So we actually considered that. Yeah, sure.
Okay. That's great. And then my second question then has to deal with the conclusion that it's all in the foot. And I don't have a good argument for that, but if we're talking about really obese people, I'm having a hard time not thinking about all of the soft tissue, all of the wobbly mass that's all over the place besides the foot. And I don't even know if an obese person has an obese foot. You know what I mean? Like, I don't even know. Yeah. Right. So do you still think it's all the foot? It's like when you think about the errors that are introduced with obese individuals?
Well, okay, this is a good question. No, I actually certainly do not believe it's all the foot, but I think it actually just depends on the anatomy of the subject. So, but I do think that in particular, I mean, I did a little bit of that in this talk, but in particular, the work of Eric has shown that it is largely in the foot in let's say the normal population. And I do agree with you that the converse is also true, that Xiaoyu has shown that for obese people, there's a clear increase. So in that sense, I think both is true, I guess.
Right, okay. I just didn't know if you would think that the obesity observation could also be explained by something in the foot, that
I see.
Fat foot, okay. Or something else. Okay,
well, the piece of evidence we have to attribute some of this to wobbling mass is actually these changes in the residual force, right? Because if there's a structure in the body that's deforming but it has no mass, then it will not contribute to discrepancies between force and motion capture.
I didn't pay so much attention with how the residual force was calculated, but I feel like if I was going to do it, I would you'd kind of do an inverse dynamics approach, and you'd go all the way up to the head, you know, and you'd figure out if like, oh, is there force on top of this person's head? And if there is, then you have some residual forces. Can you quantify residual force at every, with the analysis, can you quantify the residual force at every joint level? So you could see, oh, it's the wobbly mass of the thigh that has this much residual or energy dissipation. Can you do that?
Yeah, so that is actually a tricky point, because so the mechanics equations F equals ma actually only tells you what happens with the body as a whole, but it doesn't tell you, right? So F equals ma for the whole system is basically the ground reaction force plus gravity equals the acceleration of the center of mass. And this acceleration of the center of mass comes from basically your estimate of the individual segment center of masses, right? You do some sort of weighted average of the segment center of mass, and then you differentiate that twice, and that gives you the acceleration of the center of mass based on your kinetics, or sorry, based on your kinematics. Yeah, and then there is a difference between that quantity and the force that you measure on the ground. And basically that is the residual force. And of course you are right, if you were to compute your inverse dynamics from the foot and work your way up to the head, then exactly that force is the one that is appearing at the head.
Thanks, thank you.
I see, Tim, you have a question for Koen?
Yeah, thanks for the great talk, Koen. Really enjoyed it. I guess I was curious about the foot as well, like which part the foot contributes. And then Eric suggested it's 60 to 70%. But if I look at your data, it seems less than 50. Can you maybe go back to the graph where you showed soft tissue as a function of speed?
I can certainly do that.
Yeah, so my question is, do you think that's error, or do you think that's your anatomy? Because I think you had only yourself as subject, I guess. So that might just be,
yeah, that's correct. Yeah.
Might just be your specific
yeah,
anatomy.
So frankly, in terms of this, I would I mean, I wanted to address this because I can do this analysis with these data, but I would frankly fare more on Eric's work here, because that was just, that's a published study and involved many more subjects. So, yeah.
I see.
So I would say that maybe perhaps this, what I show here is a lesser percentage than what Eric has shown in his work. And yeah, but I would not necessarily say that this is in great conflict or that either one of us is right. Let's say, if anyone, it's not me.
Okay. Okay. My second question was about the lack of increase from the second highest speed to the highest speed. Is that also a thing that you just think is weird in your data, or is that something you believe is real?
I actually looked at it. Yeah, this is a quirk in the data. It is what it is, but this is just, I mean, of course, when you're looking at a single subject, you have some variability there.
Okay.
Yeah.
Okay, thanks.
Sure, thanks.
Hansel, please go ahead.
Yeah, Koen, thank you for the talk. And I will try to replace your definition of the soft tissue work and then ask a question after that. Yeah.
Can you speak up, please, a little bit? I don't hear you.
Do you hear me better now?
Yes.
Okay, cool. Yeah, I will first replace your definition of soft tissue work, and then we'll ask a question after that.
Okay.
So it sounded like what you are doing is something like, so you calculated joint work from your data. And let's say, as an example, let's say your joint did work, but it didn't show up in your joint mechanical energy. Then you conclude that, oh, there must be a dissipative element in your system that is not modeled. Is that how you do it?
Say that again.
So is it right that you are looking at the, say, expected effect of your joint work and external work on the change in the mechanical energy of the segment? And then if you say get less mechanical energy change, then you conclude that, oh, there must have been a dissipative element in the system. Is that how I can understand the soft tissue work?
I guess so, yeah, I guess so.
Okay, then my question is, does it mean that you should be able to measure all the forces so that you can see the joint work from that unmodeled, non-modeled element? So maybe as an example, imagine you have a meshless damper, the usual example, between some segments of your body, but you cannot really measure the force, I guess, because that's like an internal force that's happening in between segments, and then action reaction will cancel out the effect when you measure it from the force plate. Then seems like that work will not really show up in either joint work or external work, and not even in the mechanical energy change.
I see. I guess that must be correct, yeah. So I think if I just want to recast your question, I think you're saying that imagine you have some sort of a massless damper, whatever, in your elbow joint or so, and you're moving your arm. Can I then back calculate that? And I think the answer is probably no, because if I have a massless damper here, yeah, unless I know the damper properties, I'm not going to get at that, I think, yeah.
Then maybe it was helpful that your air pump was interacting with the force plate, not between your segments.
Sure, yeah, sure, yeah. Yeah. Yeah, so if you imagine the situation, if I keep the air pump in between my hands and I start doing this, and then the question is, can I back calculate the amount of energy there? Then of course the answer is no. Yeah. Yeah.
Okay, I see, Benno, you have a question for Koen?
And thank you very much. I enjoyed your talk very much.
Thanks.
When you talk about the effect of soft tissue, then I think there are two effects that you have to look at. The one effect is the deformation, like your pump illustrates, and the other effect is the wobbling effect. Now you have talked about the deformation quite a lot, but you have not talked about the wobbling effect. And the wobbling effect can be quite substantial. And if I remember correctly, Gruber in 1987, in her thesis, calculated that the reduction of joint forces due to the wobbling of the soft tissue is in the order of magnitude of more than 100%. So isn't that an aspect that should be considered too?
I would certainly agree with that. Although I beg to differ on your contention that I did not talk about the wobbling effect. So I believe that, so for me, I think that any wobbling should be appearing as a residual force, basically, because that's a disagreement between your rigidity assumption and what actually happens. And you could argue that with the force plate, we measure what actually happens to the center of mass, assuming, so this is assuming that our force plate is correct, but I think we all agree that the force plate is a fairly accurate measuring device. So I think we have a good estimate from the force plate of what actually happens, really happens to the center of mass, let's say. And then any discrepancy between our rigid body modeling of the system via the kinetics and via our stick figure model, And this force plate measurement, I think, is what reflects this wobbling.
Yeah, but it could be that the one part, the deformation, is more related to these forces, while the wobbling is more related to the joint forces. I think that functionally they are different things that have to be looked at, mechanically correct, but for different purposes.
I see. Yeah, that is well possible. I have not actually carefully, so this talk focused mainly about energetics, so I did not actually carefully consider the effect on joint reaction forces or what have you of this wobbling. Yeah, that's a good thing to look at, I guess.
Now, since you did not mention the publication, do you know it?
Gruber, I do not. I believe I'm not familiar. Maybe I have. I mean, I've read a lot, so
I think you should read it. It's quite a good
Okay.
publication.
Okay,
But it was 1998 in the Journal of Biomechanics.
Okay, that's right after I was born, so I think it should be.
Yeah, she was the first one to use the term wobbling mass.
Okay. Okay. Well, this is. I will certainly look it up. Yeah. Thanks.
Okay, I see, John, you have a question for Koen?
Yeah, thanks for the talk. I think it's really good that we examine our underlying assumptions when we do these models. I have a question about the connection between uncertainties in the kinetics and the uncertainties in the kinematics. So one of the problems with soft tissue oscillation is that it also muddies our estimate of where the segments are. And I'm thinking about this in the context of some of the optimization strategies used right now, like the reduction of residual algorithm, which I think the idea is essentially let's fudge the kinematics and fudge the inertial properties so that we get forces that line up very closely with with what a rigid body would do. So I'm wondering if you think that type of strategy is better, or if we should try to explicitly adjust for the energy dissipation instead of trying to tweak the kinematics and the inertial properties.
Sure. Very, very good question. Yeah, I also thought about this. I guess my answer would be that it depends on the application you are envisioning. So let's say that I'm Brent Edwards and I'm interested in the joint reaction forces at the knee. I probably do not want to care at all about any of these residual stuff, because the best estimate of the joint reaction forces at the knee just comes from working my way from the ankle to the shank to the thigh, right? That's close to the ground reaction force. And then you do not really care about what's happening on top of the knee and whether you have wobbling masses in your belly that contribute to inconsistencies, etc. You wouldn't care. So I think that for such an application, I would actually not recommend doing some sort of residual reduction algorithm, because you might sacrifice some accuracy of your knee force estimate to improve the estimate of your shoulder, but you're not interested in your shoulder, let's say. Okay, so, and then the other extreme might be that you are interested in the whole body. So you for some reason you want to estimate whole body joint work or something. And then I think this might well be something to consider, yeah. And then yet another, I'll close with one third category where I can imagine that optimization is a very good idea is, let's say that you want to combine this with some forward simulations. Then of course it's, you can only do forward simulations in a consistent system. So I guess if you want to do some sort of, anything related to forward simulation, you would need a consistent system. And then I think optimization is a good idea. And that's also what groups like Friedel de Groot's group from Belgium is doing this type of work. Yeah. And I think for them, it's totally reasonable to do this optimization approach where you, well, just as you explained. Yeah.
Hansel, please go ahead.
Yeah, maybe somewhat related question, but I was wondering what are people usually doing, because we saw many of the inverse dynamics analysis in many biomechanics papers, but I guess I don't usually see them talking about like where to apply residual force and stuff. That's my first question. And second is whether that affects the result of the biomechanics studies.
Okay, so first question is, I obviously don't know all the biomechanics studies, but my impression is that there is that most people do not think about this. I think that's the default. And then either do not think about this or are not affected by this. And I think the last category is, let's say, people who want to estimate joint reaction forces in the knee. They are not so much affected by all of these considerations. They are more affected, I think, by, let's say, detailed anatomical model of the knee and exact location of your axis of rotation, etc. Right? If you're looking at joint moments and things like that. And then there's a third category of people who do think about this, and I think they are most predominant in the forward dynamic simulation world, because there, of course, you need consistent systems. Yeah. And then your second question was, does it affect results? I guess this again depends on your exact question. Yeah, that's what we talked about.
So do you mean, okay, maybe let's give a question. Like if you look at the, say, knee moment before and after some surgery, let's say, maybe you will just run like standard inverse dynamics analysis on it. And maybe you may see some knee moment different before and after the surgery, let's say. But then would you say that maybe that difference just came from some inconsistency in your system or in your modeling? Can that happen, or can you get some confidence that, oh, in my case, it doesn't matter so much? Is there a way to say that?
Hard question. I'm not sure. I don't know. I think you would have to, yeah, I mean, this stuff just depends on the details of your application. Yeah, I think. But in general, my recommendation would be, the closer you are to the force plate when you're doing analysis, the less you are affected by this. That is, I think, the general rule of thumb that. Yeah.
Okay, I see Art. You have a question for Koen?
Yeah, I just want to respond to John's question about the residual force reduction. And well, first of all, I just want to say I am one of the people guilty of having considered reduction of residual forces. And that was basically to think about how to reduce sensitivity to noise in your measurements. But nowadays I renounce that idea. And the reason is that people usually are concerned about noise in terms of things like, say, skin marker artifact. And the argument is that, well, the markers don't weigh very much and they're wobbling around on the skin, and we're not interested in that. It has nothing to do with the dynamics of the body. And that would be true. Well, if it's true that the markers don't weigh anything, then it's true, it doesn't matter. But then that also means that it wouldn't show up in the residual forces. And that's because residual forces show up from some sort of mismatch in how much mass is moving and how much it's accelerating. And so if the markers really weighed 0, then they would contribute 0 to the residual forces. So assuming you have a decent force plate, and assuming there isn't a bias in your motion capture, and by bias, I mean you're measuring 1 meter of displacement and it's really 1.1 meters, something like that, then any residual force has to be attributed to something real that happened, that you can't capture with a rigid body model, and inverse dynamics is a rigid body model. And so, especially with the evidence that we have of distal foot power and Koen's experiment, we know that the body is not rigid. You know, some people estimate the body is 70% water. And so that's the most likely issue when you have residual forces. So I don't think it's a good idea to try to drive those forces to zero. Those forces are telling us that we definitely don't know something else that's happening.
I see, Walter, you have also a question for Koen?
Sure, I have a couple of questions and maybe a little comment there. Well, congratulations, Koen, for winning that free drink at the bar in Calgary for your dancing ability. I had the pleasure of seeing you dance at the ISB banquet, and I must admit, it's a sight to behold. And if you have never danced with Koen or see him dance, make sure after the pandemic you go to a bar with him. It'll be an unforgettable experience. So the question that one of the questions that I had is, you know, this is an energetics talk, and I was wondering if in your experiments you actually ever try to estimate the energetics also with oxygen consumption measurements, and whether or not the physiological energetics requirements would roughly match what you would predict happens when you add, for example, the pump to your feet there, mechanically speaking. So do the mechanics and the physiology roughly match up?
This is, I think, yeah, I would love to do that. I think, so the short answer is I didn't do it, so I don't know, but I think this is an excellent point, yeah.
The other question that I had, I was a bit surprised, you know, that the soft tissue power kind of that you calculated, if I understood you correctly, increased with the increasing speed. And I was wondering if that's going further and further, because I'm thinking also about wobbling mass, about muscles, and there, when you go harder or faster, you produce more force, which means they become stiffer. So the wobbling of them would be very different when you go faster and faster compared to. So I wonder actually if there is a maximum of that power that you lose due to the wobbling mass, or if it's an increasing function and will go on forever as you go faster and maybe even as you run. Do you know that at all?
That's a good question. I wouldn't know that. Well, so one thing to consider here is that as you go faster, your strike frequency or your step frequency increases. And so even under the assumption that each step you dissipate the same amount of energy, the power has to go up because you have to do that in a shorter amount of time. So that's one reason why this power would increase with speed, I imagine. And then another reason is, of course, that if there's anything to do with deformation, if you have larger forces acting on your system, this deformation will be bigger. And then I guess the third thing is related to wobbling masses. Actually, I guess the same applies. So if you have high ground reaction forces, you have large relatively accelerations of your center of mass. And this will lead to, so any tissue that is not rigidly, or let's say that your cheeks are sort of not very rigidly attached to your head. Now, if your head makes a very fast acceleration, then your cheeks will move in a, will move more than when your head has a small acceleration. Mm-hmm. So I do expect that for larger forces applied to the system, this wobbling is also exacerbated.
Okay. Can I jump in here real quick? Is that all right?
Yeah, of course. Yeah.
So Walter, Matthew Payne, he does research in the UK, has done some really interesting research with applying motion capture markers all over like the shank segment in order to estimate this soft tissue absorption that's going on. And he saw with heel striking runners that from 11 to 20 kilometers per hour, that there was an increasing amount of soft tissue absorption. But with forefoot striking runners, it basically bottomed out, which is interesting. Also, in terms of the absorption performed by the foot in the shoe, I've done these estimates in running as well, and I have yet to see basically a bottoming out effect with the soft tissue absorption going on in the shoe.
Okay, interesting. Yeah, I would have just intuitively expected that it would flatten out and then maybe even go down as you run, if you run 100 meters full speed, but maybe not. And the last question that I had is, if I understood you correctly, you said that in your measurements there that you had, you overestimated the soft tissue power loss compared to what you expected, because you had the pump that you measured, individually how much you should have lost, but then in the actual measurement you lost more than what you predicted. Is that correct? Did I understand that correctly?
Yeah, that's correct.
Yeah, and then you said maybe that's due to some, other tissues that are involved. But then when I looked at your regular walking, there seemed to be very, very little difference or very, very little loss. And if I added that little loss to what you had predicted there, it would not make up at all what you had predicted. And so to me, that was kind of an inconsistency.
Sure. Yeah, so this is, I also noticed that, but this is actually, so this is not very large. We can go to, well, I can tell you, so this inconsistency it's a couple joules, let's say, per step.
Okay.
Which I do agree, it did not actually add it up exactly. And so the short answer is, I don't know why this happened. And the long answer is that I can imagine that actually when you are walking with these air pumps, your whole stride pattern looks a little bit different. So your kinematics are slightly different, etc. You're moving your arms around a little bit more to maintain balance. And so I can imagine that those kind of things contribute a little bit to this difference.
Yeah.
That's one thing. And another thing is that so you saw the movie of how I estimated the air pump work per one compression, but you can imagine, well, I don't know a lot about fluid mechanics and stuff like that, but you can imagine that the amount of energy that is dissipated in the air pump is probably dependent on exactly how fast it is compressing, etc., etc. So so this is in that sense not a this is not a up to the joule accurate thing, I would say.
Yeah, and just maybe a very tiny comment, and I mean it good, and that it goes kind of back to what Benno was saying, because the first time I heard about wobbling masses was actually in a seminar by Karin Gruber and Dr. Ruder, and then Yachin Deno, my MSc supervisor, and in Benno's lab. There was wobbling mass work going on in the 1980s and 1990s, and I was very surprised that none of that was mentioned. And I think it's always good to kind of go back to the origin of those things. It reminds me a little bit when sometimes people give me credit for the cross-bridge theory, and I always go, no, I'm just repeating what other people have said, So I think it might be good just for like a historical perspective to make sure that you're also a little bit of aware of the initial works that were done there.
I wholly agree. Thank you. Yeah, that's a good point.
Tim, do you have a question for Koen?
Yeah, well, I have one remark about what Walter just said or suggested. Is that I'm writing a manuscript right now about soft tissues as well. And we see at very extreme step lengths, a little bit less soft tissue work than we predict from a simple walking model. And so far, I don't have a real explanation for that, but it might be the muscle stiffening. That would be one of the potential explanations, the muscle stiffening that Walter suggested.
Because, as I said, when you exert more force, the muscle becomes stiffer, the mass is about the same, so the vibration aspects would different. I wonder if people have ever thought about that. But that's very good if you do that, Tim. I think I like that.
Okay, would there be any last question for Koen?
Let's have beer.
Yep, so that I can see you dancing.
We want to see him dance.
Yeah, it's breakfast time, Koen, where I am.
Oh, really?
There's never a bad time to dance, Rob.
I was thinking of the beer, Walter.
Oh.
Okay, on that note, I would like to thank again to Koen for sharing his work with us. Next week, we will be hearing from Dr. Venus Juma, and the title is X-ray diffraction patterns of skeletal muscle, a peek at the structure of sarcomeres after active stretch and shortening. Hope you enjoy the weather outside, maybe with a beer, as Koen said, and I'll see you all next week.